What is the golden ratio? Examples found in nature and art. Since the beginning of time, the well-known Fibonacci sequence has been a source of fascination for mathematicians, artists, designers, and scientists alike. In addition to being referred to as the golden ratio, its pervasiveness and remarkable functionality in the natural world are also indications of its significance as a fundamental defining property of the universe. Even though we have already discussed the Fibonacci sequence and the golden ratio, it is still important to recap them briefly. What follows is the beginning of the Fibonacci sequence: 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on until unending. The sum of the two numbers that come before each number is the value of that number. Even though it is a straightforward pattern, it seems to be a form of numerical system that is inherent to the universe. Here is a list of 14 incredible examples of phi found in nature. When Leonardo Fibonacci was calculating the optimal expansion pairs of rabbits over a year, he came up with the sequence that we know today. From the microscale to the macroscale, and down to biological systems and inanimate objects, its emergent patterns and ratios, phi equals 1.61803, can be observed in the present day. Even while the golden ratio does not explain every structure or pattern in the world, it is undeniably a significant factor in the development of the universe. A few instances are provided here. Number 11. Floral petals. Using the Fibonacci sequence, one may reliably determine the number of petals that are present in a flower. The flower, which has 3 petals, buttercups, which have 5, shown on the left, the chicory, which has 21 petals, the daisy, which has 34 petals, and so on are all well-known examples. Because the appropriate packing arrangement is chosen by Darwinian processes, the symbol phi is found in the petals. Each petal is positioned at 0.618034 per turn, out of a 360-degree circle, which allows for optimal exposure to sunlight and other elements. Number 10. The heads of seeds. It is also possible for Fibonaccian procedures to be applied to the head of a flower. In a typical scenario, seeds are formed in the center, and then they move outward to occupy all of the available space. Another excellent illustration of these spiraling patterns may be found in sunflowers. There are instances in which the seed heads are packed so closely together that the total number might reach fairly high, reaching as many as 144 or even more. The sum of these spirals, when counted, tends to coincide with the number from the Fibonacci sequence. To optimize filling, it is necessary to have a very irrational number, specifically one that cannot be adequately represented by a fraction. This is an interesting fact. The letter phi is a good fit for the scenario. Number 9. Pinecones. A similar arrangement can be seen on a pinnacone, where the seed pods are organized in a helical fashion. 2 spirals, each spiraling upwards in opposite directions, make up each cone. Each spiral spirals in opposite directions. The number of steps will nearly always correspond to a pair of Fibonacci numbers that are sequential to one another. Cones that meet at the back after 3 steps along the left spiral and 5 steps along the right spiral are examples of 3 to 5 cones. For instance, those cones meet at the back. Number 8. Composition of fruits and vegetables. On the other hand, pineapples and cauliflower both have spiraling patterns that are very similar to one another. Number 7. Tree branches. In addition, the Fibonacci sequence can be observed in the manner in which tree branches produce or divide. When a main trunk grows to the point where it develops a branch, this results in the creation of 2 growth points. After that, one of the newly formed stems splits into 2, while the other newly formed stem remains dormant. Each new stem follows the same pattern of branching that was used in the previous stems. A nice illustration of this is the sneezewort. There is a pattern that may be seen in root systems and even alga. Number 6. Shells. An additional illustration is provided by the exceptional characteristics of the golden rectangle. This particular shape, which is a rectangle with the ratio of the sides / being equal to the golden mean, phi, has the potential to produce a nesting process that can be repeated indefinitely and assumes the shape of a spiral. The logarithmic spiral is a type of spiral that can be seen in abundance in nature. In the same way that the cochlea of the inner ear follows the logarithmic spiral, snail shells and nautilus shells do as well. Additionally, it can be observed in the horns of particular goats, as well as in the arrangement of particular spider webs. Number 5. Spiral galaxy. It should not come as a surprise that spiral galaxies also adhere to the commonly known Fibonacci pattern. Several spiral arms make up the Milky Way, and each of these arms is a logarithmic spiral that is around 12 degrees in angle. Even though they appear to contradict Newtonian physics, spiral galaxies are an interesting side note. As early as 1925, scientists realized that the radial arms of galaxies should become curved as they spin. This was because the angular speed of rotation of the galactic disk changes with distance from the center of the galaxy. Following this, after a few rotations, spiral arms ought to begin winding their way around a galaxy. However, this is not the case, which is why the winding problem came about. It appears that the stars on the exterior move at a velocity that is greater than what is anticipated. This is a distinctive characteristic of the universe that contributes to the preservation of its structure. Number 4. Faces. There are numerous examples of the golden ratio that may be found on faces, both human and non-human. Two golden parts of the space between the eyes and the bottom of the chin are where the mouth and the nose are located on the face of the individual. When viewed from the side, even the eye and ear itself, which travels along a spiral, can be observed to have dimensions that are comparable to one another. Although the bodies of every individual are unique, it is important to keep in mind that the averages of populations tend to point in the direction of phi. One additional thing that has been mentioned is that the more precisely our proportions correspond to phi, the more attractive such characteristics are judged to be about others. As an illustration, the smiles that are considered to be the most beautiful are those in which the central incisors are 1.618 mm wider than the lateral incisors, which are 1.618 mm wider than the canines, and so on. It is quite possible that from an evolutionary psychology point of view, humans are predisposed to prefer physical forms that comply with the golden ratio, which is a potential indicator of reproductive fitness and health. Number 3. Fingers. When we examine the length of our fingers, we notice that each portion, beginning at the base and ending at the wrist, is longer than the one that came before it by a difference that is about equal to the ratio of phi. Number 2. Animal bodies. Even our bodies have proportions that are in agreement with the numbers that are found in the Fibonacci sequence. As an illustration, the golden ratio is formed by measuring the distance from the navel to the floor and the distance from the top of the head to the navel. Several animal bodies, such as those of dolphins, the eye, fins, and tail all fall at golden sections. Starfish, sand dollars, sea urchins, ants, and honeybees exhibit striking similarities in their physical characteristics. Number 1. Reproductive dynamics. Regarding honeybees, there are more fascinating ways in which they follow the Fibonacci sequence. The most illustrative illustration is obtained by dividing the total number of girls in a colony by the total number of males. It is always the case that females outweigh men. In most cases, the answer is strikingly similar to 1.618. Moreover, the family tree of honeybees likewise follows the pattern that is considered to be characteristic. In contrast to females, who have two parents, a female and a male, males only have one parent, who is a female. In light of this, when it comes to the family tree, males have a total of 2, 3, 5, and 8 grandparents, great-grandparents, great-grandparents, and great-grandparents, respectively. Additionally, females have the numbers 2, 3, 5, 8, 13, and so on, following the same pattern. On top of that, it should be mentioned that the physiology of bees also follows the golden curve fairly beautifully. For more interesting topics, make sure you subscribe our YouTube channel and give your feedback right now. Thanks for watching.